Today, we design an image captioning system that generates descriptive text from images, clarify requirements, use cases, image resolution, language, real-time needs, and handling ambiguous images. Frame as ML task. Input is an image, output is a descriptive caption. Use an encoder-decoder framework. Image encoder extracts visual features, CNN or transformer-based. Text decoder, decoder-only transformer, generates captions autoregressively. Data preparation, captions. Remove non-English, duplicates, irrelevant or overly long captions. Tokenize images. Remove low quality, normalize, resize, model development, architecture, CNN or transformer image encoder plus decoder-only transformer for text. Add positional encoding for patch order. Training. Pre-train text decoder, language, and image encoder, clip VIT. Supervised fine-tuning on large image caption dataset, e.g., 400 million pairs, with next token prediction and cross-entropy loss. Sampling. Generate captions token by token. Use beam search for quality, consistency, and coherence. Evaluation. Offline. CIDERBLEUROUGEMETEOR on validation images. Online. Limited user feedback when embedded in larger applications. System design. Image pre-processing. Resize, normalize, quality filter. Caption generator. Model predicts captions token by token post-processing. Ensure fairness, inclusivity, and safety. This pipeline ensures accurate, fluent, and ethical captions, combining strong visual understanding with responsible language generation. The problem is to design image captioning that generates text that describes an image. What specific use cases are we targeting? What's the resolution of each image? What's the language needed? Is real-time captioning required? How should we handle images with ambiguous content? In this project, our goal is to take an image as input and generate a descriptive text caption as output. This means our problem is essentially a sequence generation task, but instead of generating text from text, we're generating text from visual input. The most common approach is to frame this as an encoder-decoder problem. The image encoder is responsible for extracting meaningful features from the input image. For example, a convolutional neural network or a vision transformer can be used to represent the image as a high-dimensional feature vector. These image features are then fed into the text decoder, which generates the caption word by word. The decoder can be an LSTM, GRU, or more recently, a transformer-based language model. It uses the image features to inform its token predictions so that the generated text accurately reflects the objects, actions, and relationships present in the image. This framing is important because it defines the type of model architecture we will use, the training objective, which is to minimize the difference between generated captions and ground truth captions, the evaluation strategy, which can be based on language generation metrics like BLEU, CIDER, or METEOR. By establishing the input-output mapping and selecting an encoder-decoder structure, we have a clear ML formulation that guides data collection, model choice, and optimization strategy. Data preparation is a critical step to ensure our model learns effectively and generalizes well. We need to carefully prepare both the captions and the images. Starting with caption preparation. First, we remove pairs where the caption is not in English to maintain consistency and avoid confusion during training. We then remove duplicate images or captions to prevent biasing the model toward overrepresented examples. Captions that are irrelevant to the image content are filtered out to ensure the data quality. For captions that are excessively long or overly detailed, we summarize or shorten them to keep the model focused on the main descriptive elements. Finally, the captions are tokenized, breaking down sentences into smaller units like words or subwords, which converts the text into a format the model can understand. On the image side, we remove low-quality or corrupted images that could confuse the model or degrade training performance. Images are normalized, meaning pixel values are scaled to a consistent range to help the model converge faster. To ensure uniformity in training, images are resized or adjusted to consistent dimensions, since models expect inputs of fixed size. Together, these steps prepare a clean, consistent data set where each image is paired with an informative caption in a model-friendly format, setting the stage for effective training. In the image captioning model, the architecture typically follows an encoder-decoder design, where the image encoder extracts meaningful visual features, and the text decoder generates the caption based on those features. Starting with the image encoder. There are two popular types of encoders. One is CNN-based encoders, which process the image and output a grid of feature vectors representing different spatial regions. This grid preserves the spatial structure and allows the decoder to attend to specific parts of the image when generating each word. The other is transformer-based encoders, which treat the image differently. They first patchify the image, meaning the image is divided into fixed-size patches. Each patch is flattened and then projected into an embedding space. This converts the image into a sequence of patch embeddings, similar to tokens in natural language. To help the transformer understand the order and position of these patches, positional encodings are added. These can be 1D or 2D and either fixed, like sinusoidal, or learnable embeddings that provide spatial context to each patch embedding. On the text side, the text decoder is typically a decoder-only transformer. It takes the sequence of image feature vectors from the encoder and autoregressively generates the caption, predicting one token at a time. During caption generation, the decoder attends both to the previously generated tokens and the image features, allowing it to ground words in the visual content. This architecture leverages the power of transformers for both visual and language understanding, making it well-suited for the complex task of generating descriptive captions. Training an image captioning model typically involves two main phases: unsupervised pre-training and supervised fine-tuning. Unsupervised pre-training, the text decoder can be pre-trained on large corpora of general text data to learn language structure and fluency. Often, we leverage existing pre-trained language models, which saves time and resources. Similarly, the image encoder can come from pre-trained vision models such as CLIP or Vision Transformer, VIT. These models are trained on vast image datasets to extract rich visual features. Using pre-trained encoders provides a strong visual foundation. Supervised fine-tuning. After pre-training, we fine-tune both the image encoder and text decoder together on a large paired dataset, such as 400 million image caption pairs. This step aligns visual representations with natural language descriptions. The machine learning objective during fine-tuning is next token prediction. Given the image features and preceding words, the decoder learns to predict the next word in the caption sequence. We optimize the model using the cross-entropy loss, which measures the difference between predicted token probabilities and the actual ground truth tokens, encouraging the model to produce accurate captions. This two-stage training strategy leverages prior knowledge from general language and vision tasks, then adapts it to the specific image captioning objective, enabling efficient learning at scale. In the image captioning system, generating a caption involves producing tokens one at a time, based on the image features and the tokens generated so far. This sequential generation allows the model to build a coherent and contextually relevant sentence. A widely used decoding strategy here is beam search. Instead of greedily picking the single most probable token at each step, beam search maintains multiple candidate sequences, called beams, simultaneously. This helps in balancing quality and diversity during generation. The benefits of beam search include quality. It improves the overall quality of captions by exploring several possible token sequences and choosing those that score highest in likelihood. Consistency. By keeping multiple candidate sequences, beam search avoids early commitment to suboptimal words, leading to more consistent sentence structures. Coherence. Since it considers the broader context of the entire partial sequence, beam search helps generate captions that are more logically coherent and natural sounding. Overall, beam search is a practical and effective approach for generating accurate and fluent captions that faithfully describe the content of the image. Evaluating an image captioning system involves carefully measuring how well the model can generate accurate and human-like descriptions for images it has not seen before. We primarily rely on offline metrics, supplemented by limited online feedback. Offline metrics. The evaluation uses a validation dataset consisting of images paired with multiple high-quality, human-written captions. These examples are unseen during training to provide an unbiased performance estimate. A key metric is CIDER, consensus-based image description evaluation. CIDER works by representing each caption as a weighted vector of n-grams using TF-IDF, term frequency inverse document frequency. This weighting highlights unique and relevant words, reducing the influence of common, less informative words. CIDER then computes cosine similarity between the generated caption and the set of reference captions, aggregating these scores to assess how closely the model's output aligns with human consensus descriptions. This makes CIDER particularly sensitive to both the relevance and specificity of generated captions. Other widely used metrics include BLOW, which measures n-gram overlap precision between generated and reference captions, ROUGE, emphasizing recall of overlapping sequences, and METEOR, which improves upon BLU by incorporating synonym matching and stemming, providing better correlation with human judgments. Together, these metrics provide a quantitative assessment of fluency, relevance, and informativeness. Online metrics. Collecting online user feedback for image captioning can be challenging because captioning is often a component within broader applications, making direct user interaction and explicit feedback sparse. Nonetheless, when possible, user engagement and qualitative assessments can supplement offline metrics to ensure captions meet real-world expectations. In summary, CIDER stands out by leveraging TF-IDF weighting and consensus scoring, making it a powerful tool to evaluate how well the generated captions capture the important distinctive content in an image. Combining CIDER with other metrics gives a holistic picture of model performance. The overall system design of an image captioning solution involves multiple interconnected components working together to generate accurate and responsible captions. 1. Image preprocessing. This component prepares raw images for the model by performing tasks such as resizing, normalization, and quality filtering. Proper preprocessing ensures that the images fed into the encoder are consistent in format and quality, which is critical for effective feature extraction during training and inference. 2. Caption. Generator. The core of the system, this module uses the trained image captioning model, combining an image encoder and a text decoder to produce captions. Given an input image, it extracts visual features and generates a descriptive caption token by token. Beam search or other sampling techniques are often employed here to produce fluent and coherent sentences. 3rd, post-processing. Once the caption is generated, this stage applies fairness, inclusivity, and safety checks. It filters out potentially biased, offensive, or inappropriate content, and may adjust language to ensure respectful and inclusive descriptions. This step is essential for building trust and ensuring the system's outputs align with ethical guidelines. Together, these components form a pipeline that not only generates high-quality captions, but also addresses real-world considerations of fairness and user safety, making the system robust and trustworthy.